one common assumption that we have is the normal distribution or Gaussian distribution. So this is what Gaussian distribution looks like to those of you who haven't taken stat yet. The two parameters that we are configuring here in normal distribution is the mu or the mean and the variance or standard deviation. Well, it's really just the same because you are just applying squared to the standard deviation for it to become variance. But yeah, you get the idea. So if you have, say, for example, a mu of 0 and a variance of 0.2, the graph will look like this blue one here. It's very tall. But if you increase the variance, like this one, this red curve, you'll see that it will become more spread out. That's what variance does to this equation. Of course, if you move mu, then it will be shifted. So the green one is here. You get the idea. The higher the variance or standard deviation, the more spread out your curve will look like. And if you change the mu, then the graph will shift to the left or right. That's Gaussian distribution. And many things in nature follow this distribution. That's why it's a very common assumption in many algorithms in machine learning. So this is the whole equation for Gaussian function. I don't have to really explain this, but yeah, this is it. So you'll see that the parameters are the following: the standard deviation, this one here, and the mean. Again, standard deviation is just the square root of variance. So yeah. How about this one? It's just pi, so it's not really it's not a parameter. This one here, this x, is the specific value of our feature. So say, for example, I have an x value that is here, say -1. The probability of that to happen is around 0.1%. So that's what happens when we plug it in, this Gaussian function. But if our x value is 0, we'll have this probability 0.9 for the blue curve. Still following? Yes? No? No questions? No questions about stat, about Gaussian distribution? Basically, this is just one assumption that we have when creating our naive Bayes model. There could be many distributions. I'll show you another one later. Okay, so as I mentioned, we only need to estimate the following parameters: the standard deviation and the mean. And they're very easy to compute. So how do you get that? You simply get the standard deviation of values for feature I having class y. And this is going to be the value for this parameter here. And for mu, same, you just get the mean. And you just plug them in that equation, and then that's it. If you have mu sample, you just get the feature value, you plug them here, and you'll get the probability value for that specific feature. And going back, once you have that, you simply plug them here in this equation. So the probability of that specific feature given y, and this one is very easy to compute, the prior probability, you just add them all up after applying log transformation. And then that's it. That's your prediction for your class. Very, very straightforward. Another assumption that we could use is multinomial distribution. I think this is more familiar to you guys because this is what's being used in NLP. And the assumption is very, very simple. So the probability of x given y is just the proportion of the occurrence of that feature value over the total count. That's just it. But this works for discrete features like bag of words in NLP. It doesn't really work for many continuous values. You could try to use that, but it won't work well. That's one assumption for using this type of distribution. But normally we don't use this normal um, proportion equation. We use this instead. We apply smoothing. Why is that? Because in some cases you'll have zero counts in some of your features, and what will happen is if you have a zero count, all of them will become zero now because zero times anything will be zero, right? So, and that will be very very bad to your model. Say for example, you have text data, and what's a popular example? Spam classifier. Um, Say in that specific email, you see many red flags. You see lots of text that um, normally appear when it's a spam, but it's just that one um, token or one word that should be in a spam is not there. So will you um, basically say that it's not a spam because of just that one missing word? No, right? It will have a lower probability, but you won't immediately say that it's not a spam. So that's basically the intuition for this smoothing. If you apply a an alpha value of one, that's called applause smoothing. So yeah, you just add this alpha and and it's the number of features. So yeah, it's just a smoothing value to handle those cases, the zero counts. Right? Any questions? I guess one tip for using naive basis, if you have mostly continuous data points as your feature, then it might be best to use this, the Gaussian distribution. But if you have like discrete values, like here, discrete features, like bag of words, then use multinomial distribution. It's made for that. There are more commonly used distributions. They're just the more common ones. Bernoulli is just a specific example of multinomial. It's just two classes. In multinomial, you don't have that assumption. You could have so many classes. Okay,